Hello and welcome to Eng Phys 2P04 Lecture 30, Additional Beam Resonance Problems. We're really going to be solving the same kind of beam resonance problems we were solving before. I'm just going to give you some tools to solve them faster, namely those two-dimensional approximations to 3D that we were introducing in Lecture 18. So you've also dealt with this a little bit in the most recent tutorial. So how do we deal with two dimensions in FlexPDE? How can we use the same equations that we've developed for 3D and solve two-dimensional problems? First way to do it is to say, let's use the plane strain condition, which is to say there's no strain in the z direction. And to do that, all you do is, in FlexPDE, you set up Cartesian 2 at the beginning, comment out everything involving that requires a w in it, and instead of saying that Ez is equal to the derivative of w with respect to z, and using the equivalent definitions for gy, z, and gx, you just set them equal to 0. Then you can use exactly the same equations as before. You don't need the w equation anymore. And in the u and v equations, because there is no z, you just need to get rid of these derivatives. Okay? That should be justified because as long as it's symmetric in the z direction, there's no, or rather constant in the z direction, there's nothing going on there, then we don't have the ability for anything to change in that direction. And now everything works great. You can solve problems using this in 2 dimensions, and it should match the 3-dimensional case if you were to say that there's no stress in the, or rather no strain in the z direction. Okay. Now, the plane stress condition is a bit more complicated. To substitute that into FlexPDE, you can't just say that the stresses are equal to 0, because the strain that results in the z direction will not necessarily be 0, and those affect your x and y stress equations. So what we need to do instead is say, not really say that the stress is 0 directly, but say that the equations we know are equal to stress are 0, the last 3 of the constitutive equations multiplied out. Then solve these 3 equations for the z strain terms, all of the strain terms involving z, these 3, and then substitute that back in. Instead of the definitions of those strain terms involving derivatives that involve w, we just substitute in the strain terms involving the other strain terms. So we solve these equations, these 3, the Hooke's law equations for the stress involving z equals 0, for the strains involving z, there they are, and then use those as our definition of those strains. It looks messy, but you can just copy this into FlexPDE and then it'll solve. So first let's check the results, kind of from a theoretical perspective. We found that for an isotropic material, we had the stresses are related to the strains like so. Do we get the same result from this set of equations in Maple? Okay, so we have to substitute in the coefficients of an isotropic matrix. If you do this, an isotropic material's stiffness matrix here, substitute it in, and then try and do the same solving as we had before. Assign the results of that solving, and then look at the other 3 Hooke's law equations for the stresses. We come up with these expressions. Sure enough, these are equal to these in terms of the x and y stress. You can multiply the matrix out if you'd like to see that a little further. All right, so let's look at these 2D approximations to a 3D cantilever. Let's first try this cantilever with a fixed load. So we're not going to be doing a resonant mode type thing. We're just going to be looking at cantilever displacement and see if you can apply appropriate boundary conditions to this cantilever by building it in 3D and compare with using these 2-dimensional approximations here. Doing that, I find out for the 3D case for plane stress, meaning load in the w direction equals 0 on all surfaces, these displacements at the end. And for our 2 dimensions, a little bit different. Not very different, same kind of order of magnitude, but a little bit different results. And for plane strain, results end up being quite on point. So the plane strain approximation seems to be closer to the 3-dimensional case than the plane stress approximation of that is. Okay, let's try some resonant modes. So use the 2D plane stress setup to check the fundamental frequency we found for the cantilever in lecture 28. And remember to change the thickness to 0.1 in the y direction, because we don't have a z direction anymore. Okay, so we modify the equations, the equation section of the 2D plane stress to the following. And then using our solving, we come up with this. So here's our initial guess of the resonance using a very large range of frequency to start off. Zooming in on this one. So seeing that the resonance is between stage 3 and stage 4, where it's at the peak here and at this peak, we can zoom in on those values by setting the new frequency to be 10 to the power of 0.1 times stage 3, so 0.3, and then add in another 20 stages in between the previous stage 3 and 4 like this. Zooming in now, it looks like this. We can zoom in even further. So we've narrowed it down to, with the first guess, between 399 and 502. Now we know it's between 458 and 463. And continuing this way, you can narrow it down as much as you like. So between 460.8 and 461.1. So somewhere in there, right around 461 hertz. And here is what the picture of the first mode looks like. And that's it. That's what we're going to be doing with this course. So we've come full circle. We've ended up with dynamic problems in beams, kind of combining statics and dynamics, doing something that's useful, which is figuring out resonant mode shapes and corresponding resonant frequencies for real structures.